Hi, everyone. Can everybody hear me okay? Cool. Yeah, I guess I'll get started. Um, so to kind of sum up where we are. Right. We need to decide interviewer for today. I can't hear you, Paul. Still can't hear you. I still can't hear you.
How about now?
Yeah.
Yeah, sorry about that. I was going to say, given that I am not going to be able to, or no, actually, no, hold on. I should still be here for that. No, I might not be able to be here for next week, so I'm happy to do this week.
Okay, sounds good to me. Um, so yeah, to get started, I wanted to kind of sum up where we are in the talk so far. So we've gone through the definition of UDT and my three tiling proofs for UDT, one of which was for UDT 1.1 and the other two of which were for UDT 1.0. And I would say, especially after the discussion last week, I feel all three of these proofs are fairly dissatisfying. Um, like for this third proof in particular, which is supposed to be the most promising proof, we have the restricted coordination assumption is much stronger than we would like it to be. The limited self-modification assumption is also much stronger than we would like it to be. Um, and then the faith in argmax assumption is much stronger than we would like it to be. And also like the
Is that really a can't modify itself condition, or more like a there's no point to modifying itself?
here
Yeah,
or
the fine grained fairness, because that looks less like it looks less like literally can't modify itself, and more like if it modifies itself, that won't actually improve its outcome on expectation.
so fine grained fairness is like um, if we unpack the modification into the non-modifying version of the action plus knowledge that we will do the thing modified,
Yes,
then we don't change the expectation.
yes, and so
So it's not saying that you can't modify yourself, but it is saying, yeah, um there should be no reason like we shouldn't think that
the self modification itself can't give you payoff of itself.
yeah. Honestly, I think that assumption is okay out of all
Yes,
of them.
Yeah, that actually seems to me like one of the, like maybe the one closest to something we'd want to keep around. Limited
Right.
self-modification could probably be reworked a little bit. Restricted coordination, probably okay, depending on how it gets applied.
So here's my beef with restricted coordination. I'm like, it was supposed to be like the idea here was supposed to be something weaker than the coordination assumption here.
Yeah.
Which basically assumes the whole point to be proved. But although it is weaker in some ways, it's stronger in other ways, because the assumption here admits the possibility that the reason there are no coordination problems blocking the tiling is because the agent trusts itself, that it just has a good enough prior over its actions that it expects the actions to be good. It expects its
Yes.
actions to be coordinated. But the assumption here rules out any decision problems that include coordination difficulties at all.
Yes. Yeah, the
And
original, good.
that seems unfortunately stronger. And furthermore, the point that you made last time about finding like skipping a bunch of steps in the proof, I still haven't like written out a version that does that, but it seems to me that something like if we drop the P on the outside of restricted coordination and just say these two argmaxes are actually equal, and then it's like um, well, yeah, then we can't skip a bunch of steps. But if we also drop the argmaxes and say these expectations are equal, then we could jump straight from step 2 to the end by just dropping this condition.
Yes.
And so the reason that that feels like concerning to me is it's saying, well, like this is wrapping in the P and setting it equal to 1 is kind of weakening it in a sense, but it's only plausible to the extent that the thing we're wrapping in the probability statement is plausible, right? And so if this assumption is plausible, then either like we're purposefully building a diluted agent or the underlying thing that we're wrapping in a probability statement is plausible. And the underlying thing that we're wrapping in a probability statement is so close to just like short circuiting this proof that once again I feel like the coordination assumption is kind of doing too much work.
I think I agree, and in particular, I am decidedly so. What? So I didn't actually come back with a full shorter proof because I wasn't convinced that you could get one, especially with restricted coordination as is. But then on top of that, I'm not even convinced that it'd be correct to strip away. I mean, stripping away the P, whatever. Stripping away the argmax, that's kind of a problem because the more I think about it, the more I realize that if you have this additional knowledge about your agent, that might actually affect the kinds of payoffs that it gets. Because if you happen to know that, I don't know, if you the payoffs that an agent that an agent you designed to be a chef would make, if you also happen to know that it will totally just let pots boil over, will not be the same expected value as just generically not knowing whether or not.
Yep.
if you want, I can provide other snow clone examples here of the kind of thing I'm thinking of, why these two expected values shouldn't be the same.
I think I get the picture. Yeah. So the idea, as I am understanding it from you, is like fine-grained fairness. We might think it's not totally realistic in the real world, but it's a reasonable abstraction to think about these situations where we can prove a no self-modification theorem. But this restricted coordination, it seems like it's kind of throwing out a certain kind of even this other assumption, which I now kind of like better. Like both of them feel like they're throwing out a kind of question of bounded cognition, which is a really important question of bounded cognition, which is basically like how the agent plans ahead, how it thinks about its future self's actions, and saying, nope, that's just not important here. And that seems like a kind of assumption that would come to bite us later when we're trying to make these more realistic. Norman?
Norman, go ahead. Yeah.
Norman, you're muted.
Oh, sorry. Yeah, I seem to have a problem that when I can you hear me?
Yes.
Yeah.
Oh, okay. Then there's no problem. So I got a weakened version of restricted coordination. And it's just so I try to use it replace restricted coordination with my new assumption in the proof, and it almost worked. And yeah, there's some subtleties, like I need to introduce a new assumption, but it's very similar in spirit to faith in Rmax. And I think there may be something like a faith principle, like a more general version of faith to cover that. But first I should say that the weakened assumption is that you just plug a max over A2 within the after the argmax A1. I think that's a lot more that's more like coordination.
So what do you mean after the max?
Like
argmax A1, max A2.
Only on the left hand side.
Can you send an image of like how does restricted coordination in your case look like? Like publishing in the Discord channel, for example. Or is it not close to us?
I can write it now. Just write if it doesn't waste too much time, because like I couldn't take photo now. Sorry. Yeah.
Oh, okay, sorry.
But is it like clear from what I said? Like
it's clear. I think it's clear to me from what you said, what the syntactical form is. It's not yet clear to me what the implication of it is, like what the spirit of it is.
So the first thing is that this assumption, I proved that my new assumption is it follows from restricted coordination, the original restricted coordination plus faith in Rmax.
Oh, okay. It seems like
in this sense it is weaker.
Okay, right. So it almost follows, like if we drop the P, then it would follow from restricted coordination, because restricted coordination is saying for all actions, and then this is just saying for a particular one. But then with the P around it, then it's like not so clear because we're imagining these bounded reasoners. And then you need the faith in argmax to get it to work. Yeah.
Yeah, that's a very high level way of describing it. And I'm not sure if like I only have like the low level proof in my head now. So yeah. And so Roman, do you know the form now? Do I have to repeat?
Well, it would be nice. I didn't catch it.
Okay. I just so in the P, within the P, like the equality within the P, on the left hand side, I plug in a max over A2 after the argmax, after the first argmax. And if you try to, yes.
Sorry, max over A2. So you are like max of argmax? What do you mean? Or
No,
instead
argmax of max.
argmax?
Argmax over A1 of max over A2 of the
Oh,
expression.
okay.
Yeah.
While this discussion is going on, would you mind going back to the previous slide about the coordination assumption for 1.1? Or yeah, 1.0, right? Just pure coordination.
Yeah.
Need to get this. Yes, and then could you go back to the summary slide that we started off the call on? Thank you. Okay, go ahead. With the other things we're talking about, I just wanted to take some notes here.
Yeah, so argmax of A1 over max over A2 of the expected value which is already written, and this is equal to just argmax.
The same thing. Yeah.
Okay, that seems to be a stronger assumption. Like, argmax A1 P. Yeah, okay, this is weaker. Okay, this is weaker.
Yeah, I mean, it's just kind of different because it's within this P, but it feels kind of weaker because it's saying like one particular A2 instead of all the A2.
Wait, the assumption is not inside of the P. The Norman's version is not inside of the P, or is it?
It's inside.
Okay.
Yeah.
Yeah. Okay.
You haven't written down the proof yet, or have you?
Yes, I wrote it down, and I plan to write it in text tomorrow.
Oh, okay.
Yeah,
Okay,
so
okay.
I just worked it out today. Sorry.
Okay.
Yeah. Cool. So yeah, that sounds like it might be an improvement. I'm not sure yet. So generally speaking, I'm like, where we're at is I've said to some of you in one-on-ones, this talk is kind of like a number of stepping stones on a path that I haven't fully connected yet. And so what we need to do research-wise is try and work on the individual stepping stones to get them to be better until they kind of connect with each other, right? And so the ideal here would be if this was a proof that we thought could connect with the next part of the talk, which I don't think it is right now, right? So this is like let's just think about UDT in the abstract and try to prove as nice and realistic feeling of tiling theorems for UDT as we can. And then the next part of the talk is let's think about logical uncertainty and logical induction, and let's try to massage that formalism as best we can, such that we expect it to then join up with some sort of tiling reasoning. And so, of course, I have some intuitions which I'm going to express about how to do that, but in some sense, we really don't know how to do that until we have this proof that we're trying to fit it with. And at the same time, we don't know exactly what form this proof needs to take until we have this piece that we're trying to fit it with. So that's kind of a high-level picture of what's going on. And so in that sense, everything that I'm showing you is more like heuristic, like maybe these things are right to fit together, but more research is needed to figure out exactly what the form is. And yeah, as you can see, it seems pretty intuitive that what I've done so far is not going to be adequate.
Yeah, I'm still not happy about the 1.0 coordination axiom, like particularly unhappy with it. So I'm surprised that you keep saying that you're happier with it now.
I am not happier with it, strictly speaking. I am happier with it relative to restricted coordination. Like, I'm like, this coordination assumption.
It's way too strong. Just full stop. It assumes that a superior policy is pointwise superior for every observation.
Do you actually like this one better? I guess the good thing about this one is I'm at least not assuming the coordination with respect to the self-modifying actions.
Yes.
And the rest of the proof has to do that work.
I'm okay with that part. That's the part. That's not the part that I'm unhappy with. That I'm maximally happy with. If anything, I think you could probably just say you can strip off the p of this thing equals 1 and just talk about the argmax actions, because when I was complaining earlier about like the chef robot version of this,
yeah,
I would still say that the argmaxing action is probably the same in both cases. With the defective lets pots boil over one for sure, and the one where you don't know whether it lets pots boil over, you should still say that the argmaxing action for them to take, given observation 1, should be the same, even if you don't trust it around pots.
I haven't understood your analogy with spots, but if we strip away P, the proof as it is right now wouldn't work, because this like argmax assumption might hold, but if agent does not believe it, then it's like it's not going to tile. So
if we strengthen restricted coordination to bring it from probability of this thing happening is 1, marginally stronger to actually these two actions are just the same.
There is a difference between the probability of them happening is 1 and agent's prior believes that probability of it happening is 1.
Yeah, it's not strictly stronger. It's like it being true, particularly because I'm not assuming mathematical omniscience. I'm not assuming logical omniscience. Like,
right,
the argmaxes being equal does not imply that the probability of the argmaxes being equal is 1.
Right. So wait, what are we taking probabilities over then? Over like samples of observations? Over?
I'm not sure what you mean by over. I would
we have
say,
a probability of these things being equal being 1. So what's our sample space? Observations, yeah. I assume.
I would say that the sample space is worlds, right? Like worlds meaning conjunctions of sentences which determine all the facts. Like, our event algebra is just this logic that we're expressing stuff in.
Okay. Sorry. So by the way, Ramon, so for the analogy that I made about like a chef robot, I was arguing that we can probably strip away the probability equals 1, but we probably can't strip away the argmax here. So the example that I gave was, let's say that observation O2 is this pot is boiling over and I need to turn it off or it's going to ruin the soup. And in one case, you know for a fact that A2 is actually I'm just going to let the pot boil over. Or actually I will for certain always turn it off. One of the two. Then we should expect the expected value for that agent, for which we know exactly what it does for this, not to be the same as... Wait, I think I've talked myself out of this. Okay, so I think for a general agent, these might not be the same, but now I'm thinking about, hold on a second, or pi star comes from an argmax process. So it should never be taking some action that...
No, sorry, I think that this is related to my weakening, because I think I'm thinking along the very similar lines. And I noticed that what you're trying to say, like pi star being like the optimal action, it's only
Yes.
For conditioning on one observation. So in your example, I think it doesn't invalidate your intuition that this this assumption is not reasonable.
Is that true? I mean, so let me just finish explaining what the
Okay, sorry.
the analogy was. No, it's okay. Sorry, I think I agree with you, Norman. I just want to make sure to explain the rest of this to Roman and whoever else listens later on. The idea here was our expected values here should not be the same, because leaving aside the question of whether or not this pi star is some optimal policy in some sense, if A2 is an action that's known to have bad payoffs, or it's known to have good payoffs, or something like that, then we should expect that our expected values for those two, like those two expected values, I can't point at it because I'm not pointing at a whiteboard here, but the expected value of U given O1 and O2, and then expected value of just O1 there, those two shouldn't necessarily be the same. Even if it is the case that your argmax over A1 is the same. And the example that I gave, like the example that I continued on with, was maybe this chef robot is really, really good at peeling and cutting vegetables. Like full stop, don't worry about it, very good at that. So you should give it observations such that, you should put it in situations where the observation it gets is, I need to cut these vegetables, or there are vegetables in front of me. And even if you don't trust it around pots, because you know for a fact that they'll boil over if you just leave it alone with the pots, your argmaxing action or the chef bot's argmaxing action for O1 is going to be identical, even if its expected payoff is not.
Yeah, and that's why stripping off argmax A1 is strengthening the assumption.
Significantly.
Yes. To the point that it's maybe not even valid anymore. In the same way that I keep arguing that the 1.0, the like full flavor coordination, is probably not actually valid.
I'm not sure. Again, I'm like, you're calling this like valid, invalid. I'm like,
I'm saying it's not justified because there are these very simple toy examples that immediately break them.
right, but like, if the assumption is ruling them out, there's not a black and white question of whether that's valid or invalid. It's just like the proof is applicable in much less circumstances or much more circumstances. Right, like,
I'm saying that one of the load-bearing assumptions of these proofs, like the ones for UDT 1.0, for instance, one of the load-bearing assumptions is something that we shouldn't actually expect to be true. One policy can be better than another without being better point-wise.
All of the load-bearing assumptions are things we shouldn't actually expect to be true. Like faith in argmax, or sorry, like fine-grained fairness is like the most plausible assumption, and it's still not going to be literally true of the actual like system that has a realistic perspective on the universe. It's just going to be like pretty closely approximately true.
Yeah,
In
and that's
particular, this isn't going to be true if humans are actually watching to check whether it self-modifies or not, because then there's a significant part of the environment that cares about.
actually, yes. But I mean, I at least feel like the case where we're looking for, does a thing on balance self-modify, then it definitely seems reasonable for me reasonable to me for one of our assumptions to be, and also the universe doesn't care about the actual literal fact of whether or not you self-modify, because at that point you can put as much of a thumb as you like on the scales. But
Yeah.
the same is not true for actually we're going to just assume this thing where there are reasonable toy setups where it just fails.
Yeah, I agree with that statement. I just I think valid is like the wrong way to say it. Like,
What way would you recommend? Justified?
I mean, maybe it's because I'm so like trained in logic, and so to me, validity is a specific thing. I think reasonable is a very good word. Like, this assumption is very unreasonable.
Okay. Then
And
yeah, I guess I would call both of those coordination assumptions implementationally unreasonable.
and then like the version where we drop argmax is even more unreasonable. Yeah, okay. Maybe we've spent enough on this.
Yes. I'm not doing a very good job at keeping us moving.
So, yeah, as I was saying, so I'm kind of moving on to the next stepping stone, this question of how we deal with computational uncertainty. I'm not sure, we might be able to move a little faster through this part since many of you have been reading up on things like logical induction in the meantime while we've been getting through the first half of this talk, but we'll see. So first I want to kind of ease into it by talking about this philosophy called radical probabilism. So radical probabilism is a philosophy that Richard Jeffrey came up with that is questioning some dogmas of regular Bayesianism. I don't want to call this a non-Bayesian philosophy because it seems important to me that Bayesian really should properly mean subjective probabilism, right? Like, probability theory is good. In particular, probability theory is good for talking about subjective belief states. That's kind of the core definition of Bayesianism. But typically, Bayesianism comes bundled with the dogma of Bayesian updates. The idea that Bayes' law is not just a theorem that we can prove about probabilities, but is furthermore it dictates how we should move from one belief state to the next belief state, right? And of course, we already are kind of seriously questioning Bayes' law in that way or seriously questioning Bayesian updates with updateless decision theory. But Richard Jeffrey dislikes it for a very different reason. Namely, he was dissatisfied with the idea that Bayesian evidence after you update on it is always probability 1. So in terms of like the writings of Eliezer Yudkowsky and the sequences, this is actually very much like the point that Eliezer makes in the essay that I think is titled 0 and 1 are not probabilities. That it seems in practice we should never be infinitely confident of something. And assigning probability 0 or 1 should be thought of as infinite confidence as opposed to some finite level of confidence. And that's in part because we're running on fallible hardware, so all of our thoughts are fallible, and in part just because it's really hard to know things. And so what Eliezer failed to notice in the sequences, and what Jeffrey noticed, was that this implies that Bayesian updates are problematic because they're always updating to certainty. And so he wanted to handle uncertain evidence. And if you look into the Dutch book justifications for all of these probability ideas, there is what's called the diachronic Dutch book argument for updating according to Bayes' law, but it requires a significant extra assumption that isn't needed for the Dutch book arguments for the Kolmogorov axioms. And that extra assumption is that you know already exactly how you're going to update on different observations. You don't know what observation you're going to get, but for each observation you're going to get, you know exactly how you would update. And so we could think of this as kind of planning ahead, like you planned your update ahead. And Jeffrey is basically like, well, okay, if you plan your update ahead, fine, but we don't always plan our updates ahead. We can't always think that far ahead to what it would actually feel like to be in the situation of having observed this. And furthermore, he wants to question that assumption that there are these observations. The possible updates that we might make can be indexed by these propositions which we're going to send to probability 1. Instead, he's just like, well, beliefs change somehow. We can't necessarily account for the change in belief by an observation because you can change your mind just kind of sitting in an armchair. And you can't say, oh, I observed some particular thing which changed my mind. You just maybe thought it through further than you had before. Or you had some new intuition, which we could think of like a new hypothesis entered your set of hypotheses, perhaps. And so if we follow only the Dutch book arguments, then like we get the probability theory of radical probabilism, which obeys the Kolmogorov axioms, well, with only finite additivity. Richard Jeffrey preferred only finite additivity for reasons that I more or less agree with. But yeah, basically the Kolmogorov axioms for like one time step, but then as you move between time steps, you have much weaker connections between these time steps based on you not being exploitable, like you not being money pumpable. And so you can't like oscillate your beliefs up and down forever, but you could oscillate some particular belief up and down finitely many times, and that's still considered rational.
Because eventually you cut that out
Right.
and figure your stuff out.
Yeah. And so you get this picture where you have various things that you're asymptotically not allowed to do. But at finite times, you can do any old thing and it is still rational in a broad sense. And I kind of want to defend this idea of rational in a broad sense of like, well, yeah, in some sense, the project of rationality needs to involve trying to like not make unnecessary assumptions and admit as many things as rational as can be. I think that Richard Jeffrey made a really good decision here. I think many AI type people on first hearing about this will be like, well, but why? Like, it's kind of non-constructive. Like, you're just changing your mind somehow. And so to an AI minded person, it's like, well, where does that come from? The only reason to make a change in your beliefs seems to be that you've made some observation. Richard Jeffrey is just allowing kind of reasonless or baseless changes in belief. And I think before thinking about the problem of computational uncertainty very seriously, I would have said the same thing. To me, it is mind-boggling that Richard Jeffrey came up with all of this stuff without the motivating problem of computational uncertainty.
It's not for no reason. I think I see what you're trying to aim at here. Because the idea is we've got our logical induction work, and we've got a bunch of actual programs running for some finite amounts of time, and some of them will complete first, and they provide like quote unquote evidence towards what the price of this thing should actually be. Because hey, look, here's this really quick, simple program that's meant to predict this thing's probability, and it predicted p equals 0.6. Oh no, now it's the next day, and there are a couple more programs that have enough time to run. They all seem to think that the probability is more like 0.3, so maybe it's something like 0.4 or 0.45. And now here are these even longer programs that have enough time to run, and which will probably do a better job of it, but maybe they risk overfitting, and so on, right?
Yeah, exactly.
So it's not that you're changing your mind for no reason, it's that you're changing your mind because more of these branches of inquiry are finally terminating, going, great, we have a guess, we have what we think is an answer, here it is.
Yep, exactly. And I think, to me, this is the right way of thinking of it. But what I'm highlighting is that Richard Jeffrey didn't have that idea available to him. He was not thinking in those terms of like, I have these programs that terminate, as far as I've seen. And yet he managed to hit on the right idea for that case, which is quite impressive to me.
I think I can even see why these things link up, because Jeffrey wouldn't have even been thinking, wouldn't have been modeling things at the scale of individual programs. He would have just black boxed the whole reasoning process. And so, sure, fine, if we have this black box reasoning process, and we know that sometimes it just seems to change for no obvious external reason, that's out of scope to try and figure out why. We just know that it does that sometimes.
Yeah.
But you can attempt to open the black box in any number of different ways, and one of them is we've got a bunch of programs. They have different runtimes.
Yep, right. And so I think in terms of this market analogy, again, thinking in terms of Dutch books, we can think of all these traders on a market that when their computation finishes, when they're ready to trade on the market, then they put money down on a particular thing in a particular direction. And as you guys already know, with logical induction, we can take this analogy quite far. So we have this analogy between prices and probabilities. And so what we want to do is we want to construct something that's not easily Dutch booked, rather than something that's not Dutch booked at all. One way to think about it here is like, so Dutch book arguments, as they are normally written, are again beholden to a notion of observation, because like a crisp 1 or 0 notion of observation, because in order for Dutch book arguments to be meaningful, we need the bookie to not already know anything that we don't know, because then it's obvious that it could exploit us, right? If the bookie knows which horse is going to win the race, then the fact that the bookie made money on us is not meaningfully saying anything about our irrationality. It's just saying the bookie knew better than us. And so we
you should not plunk money down with a Prussian bookie.
Right. And so
odds at all.
And so we need to restrict the bookie's knowledge to being the same as our knowledge. And then if we're exploited anyway, we say, oh, we did something irrational. We did something wrong. But in this case of computationally uncertain agents, and furthermore in this kind of more general case that Richard Jeffrey is pointing us towards, where we don't have a clearly defined notion of observation that is just 1 or 0. In that case, we can't say that the bookie knows exactly what we know, because we don't have a super well-defined notion of what exactly we know. So instead, the proposal of the logical induction formalism is basically that we rank bookies by complexity, or I should say we bound their computational complexity, so that we have some notion of what the computational capacity of the agent is, and the bookie, or I should say, yeah, we have some notion of what kind of arguments we should be able to see in terms of computational complexity of those arguments, such as polytime arguments is the choice made in the logical induction paper. And then we restrict bookies to only have that level of complexity. And then in addition, we have to not bound, but like weigh those possible bookies according to their description complexity, because even if computational complexity is restricted, if we had unrestricted description complexity, then it wouldn't matter that we had bounded computational complexity, because you could just memorize arbitrarily many computational outcomes. And so the basic idea of logical induction, you specify some language L that you're writing your beliefs in. And so the idea of the logical induction paper is we're going to specify a mathematical language such as piano arithmetic, in which we can think about a lot of mathematical theorems. We specify a class of continuous trading strategies mapping prices to specific trades. And the continuity here is going to be important, because we're going to want to take a fixed point of this later. And it also kind of gives you a certain computational class, like what continuous functions do you have access to? And then you specify a class of traders based on this computationally bounded ability to specify these continuous trading strategies. And so a trader maps a given time t to a trading strategy, and the amount of time this trader can think is some function of t, such as like we allow polytime functions.
So then logical induction as a theory is extremely underspecified, right? Because you have a bunch of different initial wealths for your traders that you can set. You have a pretty free choice of language, although it does need to be expressive enough. Your trading strategies can probably be very general. And I mean, the schedule, we've set our schedule for what we think we want for logical inductors or Bayesian logical inductors. Does that all sound correct?
Yeah, there's a lot of parameters.
Okay. And then the key is how exactly do you cut down this parameter space to end up with something that looks like Bayesian updates at all?
Yeah, indeed.
Okay. And then make sure that I'm not missing anything in the chat. Okay, never mind.
And so then I want to make sure we clearly distinguish between the logical induction criterion, which is that no trader can pump arbitrarily much money out of the market, versus the logical induction algorithm, which is the construction that shows that there are logical inductors, and it gives one recipe for building them. Right. And so I think a lot of people that have like some familiarity with the theory of logical induction will make the mistake of kind of equating these two and thinking of a logical inductor as like the logical inductor algorithm. This confusion is actually somewhat justified by a theorem of John Wentworth. John Wentworth showed that for an arbitrary logical inductor, we can view it as like as if it were constructed from this market type algorithm, where you have these traders making trades and take the fixed point of those trades. But still, yeah, I think it's important to think, well, a logical inductor could come from anywhere. It's just something that's not exploitable. And then we have this particular construction. So to say a bit more about the particular construction, at each time t, the house sets prices so as to balance the traders against each other based on their wealths. So what I mean by balance against each other is like the house has promised to give payoffs that are like if the house gives a price that is like 1/3 on this particular proposition, and then somebody makes a bet in favor of that proposition, that let's say they put $1 on that proposition, and then that proposition comes true tomorrow, then the house will give them $3, right? So it's like the amount of money put down times 1 over the price that the house initially set. And so naively, it seems like, okay, the house could be liable for some money, right? The house can lose money here. And so balancing traders against each other means that the house wants to make sure that that price is equal, or actually very close to, since we take an approximate fixed point, the ratio of money set for the proposition versus money bet against the proposition. And so we only want the house to say 1/3 for that proposition, if there's like $1 that's been bet for the proposition and $2 that have been bet against the proposition. And that way, no matter what happens tomorrow, the house is risking a negligible amount of money. It's just basically facilitating a bet between the traders.
So, question here. There's something that's not quite right about these criteria, because I would have expected this to be the house setting prices to balance traders against each other based on their stakes, not their wealths. Because they're not betting all of their money on these propositions.
Yeah, that's right, based on their stakes.
Right, but then the trader wealth should be updated on the new market prices, which should be fixed on stakes, not wealth.
So
but in turn, I expect that stake is some proportion, some nice Kelly proportion of the wealth. So it is a fixed point, just a slightly larger one than, or slightly more all-consuming one than written here.
Yeah, like the new market prices, which are themselves based on wealth, but indirectly, right? Like the stakes that are put down depend on the trader wealth.
Yes.
Because a trader can only put down money that it has. Yeah.
Yeah, I think I would, if I was going to try and write this down more cleanly, I would want to expose that part of it instead of just saying that they're based entirely on wealth, because that's just not true as stated.
That makes sense. But yeah, I'm also like brushing a lot under the carpet generally here in terms of details of the algorithm. It is a pretty long paper, and I'm certainly not going over all the details. But yeah, you're right. So, are we happy to move on from that?
I don't know about other people, but I sure am.
Okay. So the kind of the first problem in my narrative here, like the first problem that we run into trying to apply, like trying to combine updateless decision theory on the one hand and logical induction on the other hand, is, well, logical induction allows the initial belief state to be arbitrarily terrible, right? So like an early market state assigns very poor estimates to almost all the market goods. And updateless decision theory, naively, it seems it should only use the first market states. I'm kind of relying on an analogy, right? What is the prior for updateless decision theory? Well, for logical induction, the prior analog is like the initial wealths of the traders, but that's not like the right type signature for what UDT needs. You need something like a probability distribution on the propositions. And so if we're taking the initial market state, then it seems like updateless decision theory is just not going to be very good. Of course, we can mitigate this problem by running the logical inductor for a long time until the point where it has a reasonable market estimate for a lot of propositions. However, this is in some sense just kicking the can down the road, because updateless decision theory, as it specifically considering UDT 1.0, as it considers more complex observations, it's going to be conditioning on larger statements, and so it's eventually going to reach terrible estimates. And indeed, as I'm going to argue, that's going to happen like very quickly. And so my hope is to spell out extra rationality conditions on this first state, this first set of prices to mitigate this problem?
I don't move on just yet because I have two stupid questions.
Sounds good.
So, stupid question one, what does it mean for a condition to be a rationality condition? What makes a condition be a rationality condition instead of something else?
Yeah. So
Not say a coherence condition or a regularity condition or go ahead.
Well, so typically, I think at least in like AI safety circles and like adjacent, typically rationality condition is something like you better satisfy it, or you either may be exploited, or you may miss out opportunities on profit. I think that's typically how they like what's at the basis of them.
Okay, but that just sounds like some kind of maximality or no cash on the table sort of principle rather than whatever it is a rationality condition is supposed to be.
I think they are. Yeah.
Are they just identical?
I wouldn't call them identical because, for example, Cox's theorem is a way of justifying probability theory without a no cash on the table type principle.
Sorry, spelling on that?
COX theorem.
Yeah. Oh, Cox's theorem. Got it.
Yeah.
Oh, COX, not KOX. Interesting. I'm gonna dig this up later to look at. Go ahead.
Yeah, I would say, I would say it is perhaps more of a cluster than a clean definition. I definitely think this cash on the table type thing is a strong part of the cluster, but
If I can try and
something to say something a bit more general, like I feel like there's something like, well, there's a like meaningful perspective here. Like we articulate rationality conditions when we're thinking about like taking something seriously as an agent, sort of like ourselves, right? Like we're saying like these conditions are conditions that have to do with having a perspective, and a perspective has a normative flavor to it, where we're saying like something like a reasonable perspective, a perspective that could be justified or something along those lines. I do think, like, I personally use coherence conditions synonymously. Like, coherence condition is like, again, invokes in my mind, oh, there's some sort of picture of the world here, like a perspective, like it's like I can put myself in those shoes, so to speak, because it's coherent. If it's incoherent, then it's like harder to put myself in those shoes reliably, something like that. But yeah, this is somewhat messy. Really, really the question is, well, what kind of assumptions are useful for thinking about problems with AI, right? And so I'll talk in terms of rationality assumptions, but we should keep the goal in mind. We're trying to think about AI risk and AI safety, and the assumptions are useful to the extent that they're useful for thinking about that.
Okay. The second stupid question. We're working for most of the stuff we're doing in terms of some variety of logical induction market or Bayesian logical inductor that depends on a logical inductor market. And those change over time, nominally.
Right.
And also we're thinking about updateless decision theory, which famously does not.
Right. Yeah. So that's the puzzle here. Maybe that should have been the first problem, narratively speaking, but the the reason, yeah, like the idea behind thinking about Bayesian logical induction, which I'll get to in a few slides, is in order to deal with that problem. It's like, in fact, maybe I'll just go to the next slide. Like, to me, the picture that I want, like the picture that I feel is intuitively correct here, I'm like, okay, how, like, with computational uncertainty, we have this picture of beliefs changing over time. And with updateless decision theory, we've discarded this idea of beliefs changing over time. So how can we possibly bring these two together? And so I've drawn these like kind of lines. Think of this as like, market prices are oscillating. Really, this should be a big multi-dimensional belief space, but so we have our initial beliefs, and then somehow these beliefs are changing over time. We reach an intermediate point where we have reached reasonably good estimates of all of the probabilities that are going to be involved in the decision problem that we're later going to face. But these estimates are still more prior-like than posterior-like, in the sense that we haven't yet like updated on the details of the situation. We just have like a good like kind of notion of like, well, what's the future frequency of we would expect to end up in certain sorts of situations. And then as beliefs further evolve, we condition on the particularities of the situation we find ourselves in. And so we can see, for example, that a coin has landed on heads or tails. Whether it's an empirical coin or a logical coin, we somehow get that information. And then if I say counterfactual mugging, everybody knows what I mean? Question mark?
Please speak up if you don't.
I do.
Okay. So yeah, I'm thinking in particular of a counterfactual mugging here where, like, because of intuitions from updateless decision theory, we think, oh, I should assent to a counterfactual mugging, provided the payoff ratios are reasonable given the probabilities. Then I should assent to a counterfactual mugging because that's higher in expectation according to my prior probability. But here we don't have like a reasonable prior probability. And so my intuition is instead we should use this intermediate point where we've thought significantly about the problem to have these kind of reasonable probabilities, but we haven't thought so much that we've conditioned on these contingent immediate facts about the world, like whether the coin has landed on heads or tails.
So one quick question from me and a longer one from the chat that I have something to say about. First off, for a quick question, what is that middle branch supposed to represent in this picture? Like the one that branches off from the main line at the very start and then it sort of trails along. Yeah, that one.
So this is representing that from this perspective. I just wanted to remind, like, from this perspective, there are many, many different branches that could happen, right? And so, like, from this perspective, this thick branch that I've drawn is not a necessity. There are many other branches that could be the case. And we're, like, actually ignoring those. So my intuition is like, thinking of this as the prior, we should have like these probabilities over how things could evolve, but then we like we choose to only pay attention to the intermediate evolution that actually took place here, or at least like the degree to which we pay attention to branches like this are like negligible somehow, because this is the branch that reality took but then we only take that branch of reality like so far, and after a certain point, we say, okay, I don't want to be more updateful than that.
Right. For the just a moment, Matish, for the question from chat, what about the decision principle? Quote: act as a logically omniscient UDT agent would act in your place according to your best estimate of how it would act. Or in this case, prior is the estimate of epistemic state of a perfect UDT agent, which changes with the development of logical induction, not the market state of t equals 0. My snap response, I don't know what Abram's going to say about this, but my snap response there is that you immediately run a risk of ill-founded buck passing, because where exactly is you're getting these guesses in the first place.
Yeah, that's definitely not what I would say. I think
No,
that
right?
I think that's a well-defined approach. I think that if you just take the logical induction algorithm and then you take, like, for example, Solomonoff induction, which is a logically omniscient probability distribution, and you define an updateless decision theory according to Solomonoff induction, and then you use the logical induction algorithm to just estimate the probability that the Solomonoff induction UDT agent would do a certain thing, and then you just either match those probabilities or take the thing you think is maximal probability, something like that. This is a concrete proposal that's mathematically well defined.
Okay.
However, it doesn't take all the counterfactual muggings that I think we intuitively do want to take. Specifically, if this coin heads and tails is a logical coin instead of an empirical coin, so it's some logical proposition that is pseudo-random from our perspective, like then, so we humans think this omega is out there that uses this pseudo-random coin. We build our AGI according to this algorithm that we've just outlined. That AGI thinks for much longer with much more computation than us and determines that logical coin to be one way or the other. Then when omega comes down to earth and asks our AGI, hey, what decision do you make? Then it's going to refuse to pay up because it will have determined the logical coin and it will behave updatefully about it. So that's the problem I see. And this creates a reflective consistency problem. So it creates a tiling problem so that, like, this AGI that we've designed is reflectively unstable and it will try to modify itself away from that architecture as a result.
So in a certain sense, like, it seems obvious in hindsight, because like even when you start thinking about UDT, actually, like, okay, you want to be updateless from the perspective of some like idealized prior, but you need to take this prior from somewhere. You need to compute it somehow. So there is like some time for which we will need to compute it, or somebody else, or whatever.
Yeah. Yeah. And so I guess this is a picture in which, like, I've drawn it as kind of a halfway point. I imagine, like, larger, more complex problems, the halfway point is going to be further on. I don't think it's like, exactly a halfway point by any means, but the idea is to have some flexibility here of thinking an amount of time that is kind of appropriate to the problem, so that we're not using, like, in effect, we're not using one fixed prior. Instead, we're adaptively deciding on what kind of prior is reasonable for the problem. However, my picture is not actually that we adapt. I think that might be a picture we're thinking about, but the picture that I'm going to sketch here is one where we specify additional conditions on this first point such that it amounts to this, such that it makes decisions in a way which are as if we were using this intermediate point. And this is a somewhat sensible thing to expect to be possible because updateless decision theory, the way that we normally think of it, does indeed have this property that it can behave in an updateful way, provided that that's the right way to behave for the decision problem that it's facing.
So do you want these initial conditions to be kind of universal across all problems that are in like some relevant sense fair?
Yeah, something like that. And so it's like for these problems, it can solve them in this way of like reasoning how long it should think before behaving updatelessly. So yeah, this is like the general picture of what I want to get to work. Any further
But by
Yes.
well, by time, how long it should take updatefully? You don't mean literally time. You mean like not necessarily literally time or like computation time. More like I would imagine something like, okay, like what kinds of like or what kind of epistemic states should the agent achieve before it stops updating or something? In
Yeah,
some
like the picture I'm going to sketch is one where you do actually run the logical inductor for longer as the agent is alive longer in literal time. And then that produces knowledge, but then you might not use all of that knowledge in an updateful manner, right? So like you don't behave fully updatefully with respect to the latest logical inductor state that you've calculated, but rather an earlier one. And I guess the hope is that the procedure doesn't literally just run over like, oh, should I think for 1 step more, 2 steps more, 3 steps more, 4 steps more? Oh, 5 steps is the right one. Like I'm open to that possibility, but I think it's more ideal if we have these kind of generally plausible principles of these coherence conditions or rationality conditions to impose on how we think about computational uncertainty. And then as a consequence, in particularly simple cases, we can show that that amounts to zipping forward to you should think 5 time steps and then use that as if it were the prior. And so the reason why we would want that is because you want also to be able to mix and match. Like maybe one of the critical facts that you need to know in order to work with the decision problem appropriately comes in at time step 4, and another one of them comes in at time step 5. And so then you wouldn't have such a clean like I'm just using time step 5 as if it were the prior. Instead, you create this like reasonably useful belief state out of the relevant information, and we would want things like that to work as well.
All right, thanks.
So some further questions from Alexander in the chat. Continuing in the same vein, what if we take a logically omniscient agent that takes as its axioms only those axioms which are logically compatible with both states of logical coin? For instance, take axioms such that the billionth digit of pi, say, is even, is a Gödelian statement in the system of axioms, conditional and counterfactual dependency of sorts between branches of deductive process. I'm not clear that that's something you can do.
Yeah, I think axioms is like a awkward granularity here, right? Like, how do you decide what's an axiom? Or maybe the intention is like you believe any proposition that you come to prove, as long as it doesn't literally imply that this coin is such and such. But then wouldn't you be able to prove important consequences of the coin that are something you need to behave updatelessly for the decision problem? Like, how do you determine that the coin is something you should be treating in this way? I'm not saying it's a hopeless direction. I'm just saying I don't see it. I don't see how you would get something like that to work.
I mean, I'm sure saying it's probably a hopeless direction, given that there's a lot of different kinds of logical coins which can all be entangled with each other. I mean, I'm thinking about, look at the billionth decimal digit of pi and figure out whether it's even or odd, and then also look at the billionth binary digit of pi, or the 10 billionth binary digit of pi, or something like that, and see whether that's a 1 or a 0. And if I've understood this proposal correctly, you'd want for both of those to be undecidable within some logical system.
Yeah.
But I don't see how you can have both of those and still have things like basic arithmetic.
It's like you need to specify. Yeah, I think you don't have basic arithmetic. I think, like, yeah, the idea here is somehow to dance around basic arithmetic. In general, I tend to be skeptical of ideas that rely on, like, first having like the sort of updated state, the state that we would normally think of as rational, where you know arithmetic and you know all these things, and then you're trying to like remove something. I don't know. I could say more about why I'm generally pretty skeptical about those kinds of solutions, but I think it's a long story. I think that generally tends to not work out.
I mean, the issue is even that having that billionth digit of pi be itself undecidable means you have even just that one statement in isolation, I'm pretty sure makes basic arithmetic break, because
Yeah.
there are infinite series that calculate pi exactly. And if that's undecidable, then at what point do we stop being able to add together fractions?
Right. Yeah. It feels like it would have to make these very arbitrary decisions in some sort of principled way that feels impossible to me.
Anyway, I think we probably have time for one more slide.
Yeah, so this is a problem to kind of motivate the ideas that I've talked about abstractly here. So my claim is kind of we understand UDT well in the empirical case. And basically we want to try to handle the computational uncertainty case in a way that's analogous to the empirical case. And so I want to give a decision problem that motivates this idea of like, you behave partially updatefully according to some intermediate state, and show how in the empirical case this works out fine and we understand it pretty well. So I'm giving a modified counterfactual mugging. Imagine that instead of picking a fair coin, omega selects the coin bias uniformly between 1 and 0, and then shows you several flips from the coin before performing the coin flip that would determine the counterfactual mugging. Now, just saying that, this problem is underspecified because I haven't said critical details about how omega then behaves, how omega thinks about you when deciding whether you would have given it the $10. So in version 1, omega gives you money proportional to the total probability that you would give omega money, that you would give omega the $10, integrating across this uniform selection of the coin bias. In version 2, omega gives you money proportional to the probability that you deliver, that you give the $10, conditioned on the evidence that you just saw. So you can think of it as omega is simulating starting with you before determining the bias, or omega is simulating with you starting after you've seen the several coin flips. And so, yeah, I didn't spell out my calculations on the next slide. So yeah, my claim is that in version 1, we should treat this just as an ordinary 50-50 counterfactual mugging. Because if we behave updatefully with respect to these observed coin flips that omega shows us, then, and we see a bunch of tails, we see a bunch of the direction that means we don't get money, that we're just asked for money. And then on that basis, we think, oh, the probability of getting money in return is low, and so I shouldn't give omega the $10. Then we're just reducing our total payoff that omega would give us, because omega is just giving us money. In the case that it lands on heads, omega is giving us money just proportional to the total sort of number of us in the multiverse that hand over the $10. But in the version 2, where omega is simulating us after we've seen those initial coin flips, then we are able to behave updatefully about those coin flips, or like UDT says we should behave updatefully about those coin flips, because it gives us a better estimate of the coin bias, and we can drop out giving up the $10 just in those universes where it looks to us like the coin is so unfavorable to us that the $100 that omega would give us if we gave over those $10 in 100% of worlds isn't worth it. And on the other hand, when we see oh, the coin looks very favorable to us, then we can say, oh yeah, I select this branch is one in which I am going to give up the $10 because I'm getting far more in return. And so we're able to selectively make decisions based on these branches, whereas in the other case, all the decisions are pulled together. Does that make sense?
Yes, and I think it casts a little bit of light for me on why we should be so suspicious of the case you brought up way early on about successive logical coin flips that are all actually the same logical coin flip, and why on earth shouldn't you go ahead and take them up on one, and then having taken them up on one, why shouldn't you take them up on all the rest? I think from the correct point of view, a UDT agent looked at this whole setup and says, first off, the generic assumption I might make here, which is that all of these logical coin flips are uncorrelated in making a bet, fails spectacularly here.
Mm-hmm.
And then given that, wow, you sure are asking me to take on lots and lots of correlated risk.
Yeah. All right. Well, I suppose we should wrap up. Any further questions before we go? Or comments?
Sorry, I don't understand how in version 2 does a UDT agent come to this conclusion of behaving like updating on evidence. I understand why that's reasonable, but how could the UDT do this?
Yeah.
Or is that precisely the problem that we have to solve?
No, I'm saying that this is, if we just consider vanilla UDT, this is just going to happen. Unfortunately, I haven't written out calculations, but just, I mean, simplest to consider UDT 1.1 here, where we just optimize the policy. And my claim is that you can get a more optimal policy, you can get a higher expectation by selecting which universes you're giving up the $10 in, and only giving up the $10 when it's worth it in that universe, because Omega is simulating you in a way that separates out these different universes. And so the claim is just, if the Omega's prior, sorry, if UDT's prior codifies this version 2 then accurately, then it's going to accurately calculate the estimated, like the expected probability, sorry, the expected utility of this policy that decides which times it's worth it to give up the $10 is just going to be higher. Does that intuitively make sense? And so I claim this is a fact in general, that like updateless decision theory does behave updatefully when it's worth it to do so. Or to put it a different way, it only behaves updatefully. It only behaves updatelessly when there's a good reason to behave updatelessly. It doesn't just like always refuse to act like an updateful agent. It will act like an updateful agent when that's the appropriate solution to a decision problem. And it will do this intermediate selection thing that I'm talking about, where it like updates on some things but not others when it's appropriate to a decision problem. And in particular, in this kind of counterfactual mugging example, it seems to be basically that it should be as updateful as Omega in the way that it thinks about the problem.
Now I'm just thinking about the even more complicated case of this, where it's neither version 1 nor version 2, but actually Omega flips a true random fair coin first. And then how does our UDT agent act? Not knowing whether Omega has decided to behave updatefully with respect to the coin bias or updatelessly.
Yeah.
That just seems like the obvious, like, extra complication to put on here. And I don't know that it's clear what happens.
Does the agent see what the coin landed on, or
The
It
initial
doesn't
one,
know.
or like the sample one?
The initial one
initial one.
choose
Nope.
between version 1 and 2. Yeah.
Nope. Why
Doesn't
would
see
it?
that
That's inside
problem.
Omega's brain.
Yeah. And so it's like you're uncertain how Omega is simulating you.
Yes.
it depends on the utilities?
Right.
I would
yeah.
assume.
Yeah. And to make kind of a final point here, so in this case, we see that depending on how Omega is simulating you and how updateful that simulation is, we should be correspondingly updateful. So I claim something similar here, where this point that we should select, this intermediate point, should have to do with how Omega is reasoning. Like, if we're thinking of a logical coin here, then Omega has some way that Omega is reasoning about this coin could have been otherwise, even though it couldn't really be otherwise in terms of pure logic. And so it's going to do like some amount of work to make the world that it's imagining logically coherent, but then it's going to stop somewhere. And my claim is that we should stop at the same point. Like that's intuitively how I think this goes.
I don't know that. I think I agree with the overall picture, but brain's immediately spinning up cases where that's the wrong thing to do, where it's something like actually omega gives you money inversely proportional to that average probability, or it gives you money inversely proportional to the probability you get delivered given the evidence you saw, such that, well, if you try and pick the same cut your update point as omega, you always get it wrong.
I mean, yeah, but that's why you are restricting yourself to fair cases.
Well, not just fair cases. I'm restricting that claim to counterfactual muggings. And I
Yes.
think, like, if it's inversely proportional, then it's not like a counterfactual mugging.
Oh, I see. I see.
Like in arbitrary decision problems, yeah, I don't know. I'm certainly not claiming that you should just find omega in the universe and then be exactly as updateful as omega in general. Like, it depends on your relationship with omega.
Doesn't this just sort of push the problem further back? Like, what if you have a bad prior about omega's updatefulness? How should you update on that?
Yeah, right. This is similar to what Paul was saying as well.
Why it's just no prior, or like the max end prior.
So, yes, I agree with you, Norman, but I don't want to do it at this point for now. I guess I want, yeah, I think there's more to be said on this, but I suppose that we should end the call now.
Like different parts of the like the world building and the decision problem is like different parts of the AI. What I want to say. Technology one and decision problem one. It's like they need to be separated as like I guess.
Yeah, I have like a whole separate talk on this issue that I could give. So I think I'm just gonna call it there for today.
Right? Sounds good.
See ya.